All right, so a bit of a change of viewpoint. I will now tell you a little bit about the history of the ideas that led to the wonderful experiments that we're hearing about today. I'm one of the 6 people involved in the original formulation of the theory that eventually led to the prediction of the Higgs boson in the Standard Model. So I'll tell you a little bit about what physics was like back when I was a baby physicist in the 60s, talk a little bit about how we think of these ideas now, and tell you quite a bit about the history of our development of the theory. So, frontline particle physics in the 60s was surprisingly modern in that most of the tools that we have now were available. The difference is they weren't very developed. There was the Schwinger action principle, now something that probably has no meaning to most of you. There was the Feynman path integral, which is essentially the same thing except expressed in integral form. The calculational methods were unbelievably primitive. We, of course, knew about Feynman graphs, and mostly people only knew how to calculate with coupling constant perturbation theory. The renormalization theory was well developed, and there was deep concern about the 4 Fermi on interaction, describing the weak interactions, because it was not renormalizable. And of course, there was no understanding whatsoever of how you calculate the strong interactions. Certainly perturbation theory did not work. And the general result of that, at least when I started entering the physics world in the early 60s, was that people had mostly rejected quantum field theory. It had wonderful success in describing electromagnetism once you got over being upset about the idea of all your answers coming out infinite and learned how to renormalize. But no one really had any idea about how to do calculations for the strong interactions. There were the beginnings of the Standard Model. Yang-Mills theory, or Shah-Salam theory, was actually present, dating from about 1954. Sakurai had emphasized the importance of vector bosons in 1960. I was actually at a seminar at Harvard as a graduate student when he did this, and we were all very amused by the idea. We were very wrong, of course. The very important beginnings of the Standard Model, which the V minus A theory of weak interactions, without which we couldn't have put this all together, had been proposed by Sudarshan and Marshak in 1957, and in the words of Feynman, was publicized by Feynman and Gilman. Group theory was on the development. I mean, the group theory was there, but its application to more complicated particle physics existed in terms of flavor SU3, the Gilman Zweig model of quarks was just coming online in the early 60s. There was a great search for the omega minus to finish up the baryon decouplet to confirm those ideas. And as I say, the Gilman-Zweig quark ideas were present, not particularly well accepted. And there, of course, were problems about how you make fermions with 3 quarks. And the beginnings of the understanding of that idea probably started with Wally Greenberg in 1963, who proposed essentially a precursor to the idea of color. And this quark model then began to make some sort of sense. Now, a very important thing happened in 1960, which is that Nambu, along with Iana Lucinio, launched a new calculational method in quantum field theory, which is that he started by looking at four Fermi interactions, and instead of doing the usual and accepted coupling constant perturbation theory of the interaction which I've written there, look for a different approximation technique, a different way of describing that theory. And they described that, they said, let's start out with the idea that even though there is no mass in the theory, that we require that the expectation, and so there was a symmetry in that Lagrangian, it's chiral symmetric. Let's propose that the vacuum expectation value of psi bar psi is a non-vanishing constant. Now that, of course, broke the chiral symmetry. And this was something new to do in particle physics. You normally would expect the symmetry of the solutions would correspond to the symmetry of the action. In fact, that was the whole point of symmetries, our very strong tool in trying to understand the organization of elementary particles, was to write down an action, a Lagrangian, that had a symmetry that we perceived was present in nature from experimental results. So it was a very new idea to require that even though the theory and the equations had the symmetry, that the solutions themselves did not respect the obvious symmetry of the action. And solutions of that type were called spontaneous symmetry-breaking solutions. Now, you couldn't do, it was soon realized, and in fact, Nambu, Iana Lucinio realized in their first paper, that if you insisted on such a solution, like all interesting things, it didn't come free, that along with the spontaneous symmetry breaking was a penalty. And that penalty, or you could think of it as a reward, but it turns out it wasn't. But that penalty was that if you did this sort of dynamical symmetry breaking, you spontaneously broke a symmetry by requiring a non-vanishing vacuum expectation, you always found as a byproduct a associated zero mass particle. And that was turned into a theorem by Goldstone, Salam, and Weinberg, but even in the first Nambu paper, there was the essence of a proof of that fact. And the idea was a real breakthrough in terms of calculation, but the penalty was a real problem. Now, the point is that there are very few zero mass particles observed, real zero mass particles observed in nature. And at the time, we thought that the neutrinos were massless, and we knew that the photon was massless. But beyond that, there wasn't anything. We were looking for a massless particle associated with gravitation. We still are. Presumably, it'll show up someday. But I'm jumping ahead of myself. But in general, the zero mass particle required by the Nambu-Goldstone theorem was not a good thing. Well, I guess, hold on just a second. That just is out of order. Now, that was a pic. Oh, I'll just mention it. That picture, I don't know how it got there, but that's Abdus Salam. And he comes in later in the story. Now, there should have never been any doubt about the fact that there were spontaneously symmetry-broken solutions to quantum field theory. And that's much clearer now as we look back 50 years ago and we look at our understanding now of quantum field theory, particularly in this age where there's been tremendous development in the understanding of the equations of dynamical systems, which quantum field theory is a very particular, very complex example of. But let me just point out to you that we knew even then, we just hadn't exploited our knowledge. The clue was a one-page physical review letters by Freeman Dyson, which, if I recall, I meant to look it up before this talk, as I recall, it had no equations whatsoever in it. And basically, that paper observed that the coupling constant expansion of quantum electrodynamics could not be a convergent expansion. That, in fact, this series in E squared that we write down as the perturbative solution to quantum electrodynamics has to be an asymptotic series, that it cannot converge. And the reason is very simply that there has to be a singularity at the coupling constant equals 0 of the exact theory. You can't, it's not analytic under reflection of the coupling constant. And what that means, if you go through the analysis, it must mean that there are other solutions besides the perturbative solution to QED. And that is the clue, and that shouldn't have been that should not have even at the time been surprising to us. And I'll give you a very simple example of that. A very simple example of it is to look at this equation at the bottom of the page. Now, as it's written, it's a simple linear differential equation. I've taken derivatives in terms of J instead of X, which to some of you will be meaningful because G in quantum field theory, or J in quantum field theory, is what is commonly used as a source for a scalar field. Now you notice this is a very simple equation. It's a third order linear differential equation. And of course, you know how many solutions there are to it, right? There must be 3 solutions to it. Now, you can write down very easily an integral representation called Z in the form that I've written above. Right? Now, you can easily convince yourself by differentiating that expression that it satisfies the differential equation I wrote down on the previous page. So that's just, this is just simple second year or maybe less undergraduate calculus. Now, this Z satisfies the differential equation, but there's a question of how you evaluate the integral. Okay, because you notice I didn't specify endpoints. Now, if I evaluated the integral from -infinity to infinity, that would look very familiar to many of you. That looks very much like the path integral for quartically interacting quantum field theory, except there are no spatial or time derivative terms in it. But other than that, that should look familiar to most of you who've done any high energy physics. And that is the form that we commonly teach students now when we start talking about 5-4 theory. But of course, we put in the derivative terms. Now, what this is, because there are no spatial derivatives appearing in it, this is what's called zero-dimensional quantum field theory, more simply known to everyone else except particle physicists as a simple linear, the solution to a simple linear third-order differential equation. And so, however, you can easily convince yourself, just as there are 3 solutions to the linear differential equation, and the path integral representation I've written here must, since it satisfies that differential equation, probably has more than one solution, the integral from -infinity to infinity. And it's not very hard to convince yourself that the integral to -infinity to infinity for small coupling G is to the quartic interaction gives you essentially the Feynman graph, the perturbation series for this integral, but there are two other paths in the complex plane that this integral converges over. You can easily combine those paths in such a way that you keep Z real. I've written everything down so you're looking for real solutions. And those two other solutions correspond to, those two other possible integral paths correspond to the two other solutions of the differential equation, and to three, and thus three total solutions. And there's a clue to this, because you can very easily turn this into quantum field theory, and what you find is that every point in space-time can be represented by an integral like this. You have to essentially put in the spatial terms, but what you find then is there are potentially, for each point in space-time, there are 3 times 4 solutions, 12, and then there are an infinite number of points in space-time, so there are an infinite number of solutions. Okay. Now, in fact, what this is telling you is that if you construct a quantum field theory by dimensional extension, by starting in the 0 dimensions and go up in space-time dimensions, that you should expect an infinite number of solutions to quantum field theory. Now, by the way, those solutions have correspondence to what's called the landscape in string theory. But we're not going to go to string theory is forbidden here, so we won't go there. But of course, we restrict those considerably by requiring that we look at solutions that are translationally invariant in space-time and respect special relativity and all that. And that simplifies the solution set considerably. But the point is no one should have been surprised when Nambu and Yana Licinio wrote down those solutions and discovered there were more solutions than the perturbative solution to quantum field theory. I mean, after all, quantum field theory is very nonlinear, never mind the fact that it's very complicated, even if you limit the number of points. And no one should have been surprised, but we didn't think about quantum field theory that way at all. That had nothing. We consider ourselves lucky if we could write down a perturbative solution, let alone anything approaching a general solution. And this sort of analysis didn't exist. And what Nambu and Yana Licinio had essentially discovered in the symmetry breaking solutions was that there were more solutions, that you could begin to categorize them. And now, I said nothing here about the zero mass particle, because of course that's a subtlety of actually having space and time, and this integral doesn't have it. So bear in mind what I'm telling you about. Now, I wrote down these other solutions, so I won't go into them, except just to mention that, not surprisingly, there are solutions, if you look at these other paths, there are solutions where the coupling approaches 0, where they get small, but they're not the normal perturbative ones. In fact, those solutions, guess what? As the coupling goes to 0, those solutions are very singular, if you look at the Green's functions. And the reason they're very singular is essentially because of this beautiful observation that Dyson made in the one-page physical review letters. So, all right. So, in general, and again, let me skip over this because I wrote many more slides than I can cover. But in general, now let me go back to the early 60s. In 1962, Berkane gave a talk at Harvard, and I was a beginning graduate student. I'd been there a year or so, a couple of years really, and was looking for a thesis problem. And I had already, at that time, Julian Schwinger was the king of Harvard theoretical physics, and I thought of having him as a thesis advisor, and I went to his door to talk to him about being a student of his, and there was a line of about 25 students waiting outside the door. And I asked if they all wanted to have Schwinger as their thesis advisor, and they all assured me no, he was their thesis advisor. And I thought it would be wise to look elsewhere. And at that time, there was a young assistant professor who had just come there. He was Walter Gilbert, who incidentally was a student of Abdus Salam's. For that reason, Abdus called me his grand student. But I became a Gilbert student, and he said, hey, look at these solutions by Nambu and Ioannidis, and look at what Berkane has done, where Berkane has tried to describe ordinary electromagnetism in terms of a four-fermion interaction with a broken symmetry. And that was very strange, because the symmetry that had to be broken there was essentially Lorentz invariance, because you want to produce a massive particle, the photon, which is a particle that carries spin 1, and you want to produce that particle by symmetry breaking, and the only way you could do it would be to break the Lorentz symmetry of the theory. Now, Berkane said that it appeared that this theory looked like electromagnetism, but there was a big question about it, because breaking Lorentz symmetry, as you know, is both an interesting thing and a dangerous thing to do, because you're very likely to find answers to your field theory which are not appropriately Lorentz invariant. And that might be fun to find Lorentz invariance, but you certainly don't want to find Lorentz invariance when you're a young student trying to write a thesis and no one has observed it. So I looked at this theory, and I discovered that Berkane's basic conjecture was correct, that by working in a refined way with this theory, being very careful about everything and working it through, that you could indeed break Lorentz symmetry harmlessly. That is, even though there was a symmetry breaking, it didn't affect anything you could measure. And that this theory exactly emulated normal QED. So here was a theory that started out looking like a four-fermion interaction, a horrible thing, because its normal solutions are non-renormalizable. They give you a first-order answer, and after that, just forget it. There's no way you can deal with it. But that if you looked at the symmetry-breaking solutions, you produced not only a renormalizable theory, but a theory that you knew very well, the theory of normal spin 1/2 electrodynamics. And so this showed, again, an example that there were many solutions to the four-fermion current-current interaction. Now, I looked at this and I thought, wow, this is really very, very interesting, because the photon here, because of the Nambu-Goldstone theorem, must have zero mass. And so here's a proof the photon has zero mass. Now, right at that time, a little bit before, Schwinger, who was at Harvard, as I mentioned, had shown and argued that there was no reason that the photon has zero mass, except that through perturbation theory and the fact that it works and the coupling was small. Now, lots of people have been arguing around that time that gauge invariance required zero mass. And that was pretty much a circular argument. And I thought that just had to be wrong. That was very inelegant. And so, being very young, very naive, I thought, I'll use the Nambu-Goldstone theorem on normal electromagnetism to prove that even in normal electromagnetism, never mind the special case, that there must be a zero mass photon. And of course, working very hard, I produced a proof of it. And Wally Gilbert, very, very smart man, but whose interest by that time had already switched considerably to biology, so let him off the hook, but looked at it and said, well, it's a strange result, but I think it's right. And so I presented my thesis with that result, and Sidney Coleman, who was sitting in the audience, told me how badly this smelled, and convinced the rest of the committee, and I had to remove the chapter from my thesis, and out of the goodness of their hearts, they still let me get my PhD. And so I then had a National Science Foundation fellowship, and I went off to Imperial College, where I met Salam, and I started working there. But I should have mentioned one more thing, which another thing that I talked to with Wally Gilbert at that time was a very strange free theory, which has the interaction action that I write down there, basically a field that looks like electromagnetism interacting with a scalar field through a derivative interaction. So something that is free because it only involved two fields interacting, but it actually had a gauge invariance. It looked a little bit like electromagnetism. And this theory, just by dimensional analysis, turned out to have a mass. That parameter g that I've written down there is massive. And so this theory, in the end, even though it was free, took what looked like a photon and actually produced a vector meson. And I told Dave Bowler about that, who was also at Harvard at the time, and he got very interested in it. And he worked with Wally and turned it into a paper and did an analysis of this model, which is the Bowler-Gilbert model in 1962. Now, basically, this model is a reduced model of what's come to be known as a Higgs model. So in fact, all the information was at Harvard in 1962 about how to produce the model that eventually turned into the model that is used in the Standard Model, explaining how massless vector bosons can achieve mass. But we didn't pick up on it at the time. And I talked a lot about to my friend at MIT, who I'd worked with as an undergraduate, a man by the name of Carl Richard Hagen. And here is a picture of us hard at work. We were learning about classical mechanics in this picture. The gentleman making, I am sure, a rude motion, but the picture is not very clear, is Lord May of Oxford, who is now a very famous man, was Her Majesty's science advisor, head of the Royal Society, and has done really fundamental work on population biology. I'm sitting at the wheel of this car, and on the right is a young Carl Richard Hagen, and he seems indifferent, but he was very taken with this car. And when he got his PhD from MIT, shortly before I got my PhD at Harvard, the first thing he did is borrow a lot of money and went out and bought this E-type Jaguar. And he, as you can see then, was skinny, and he got much skinnier over the next couple of years paying for this thing. I was very afraid he was going to become an experimentalist, a very unreliable machine. Now, and I learned even more about mechanics from that machine with him. But in any event, by the way, there are a lot of car pictures in this, and this represents two things. First of all, we did like cars. That was a symbol of freedom in America at the time, and even then, physicists needed a lot of freedom because it was still hard to get jobs even then, not like now, but it was still very hard. You had to move a lot. But anyway, I went to Imperial College on my National Science Foundation postdoc. I was turned down at CERN, even though I had the money, which probably was a good thing, because Imperial College was a very exciting place at the time. Because of Salam, he gathered a great group around him. There again is Salam talking to Tom Kibble, you can see they were serious like we were, just not in classical mechanics. And so Tom and I talked a lot. I found out from talking to him and other people at Imperial College that Imperial College was a good place to do field theory, but it was nowhere nearly as protected as Harvard was. Schwinger produced a large umbrella, even though he wasn't very active producing it. People at Imperial College were very skeptical about symmetry breaking, even though they'd done a lot of work on it. And I spent a lot of time arguing with Ray Streeter there, who was an axiomatic physicist. And I construct, and he just didn't believe in spontaneous symmetry breaking. He said, you just can't do it. The axioms are such that they can't be consistent with symmetry breaking. And I constructed for him a free model of symmetry breaking, and finally convinced him that the axioms were too restrictive. But that then gave me boy, this is a mess. I don't know what hold on, I'm very sorry. But anyway, I constructed a model with him, and while I was at it, I wrote a paper on this model, but I couldn't let go of the idea that there had to be some way to actually prove the real photon was massless. So while I was in the process of constructing this model, in the same paper, I put in yet another proof that the real photon, the one that we describe in ordinary electrodynamics, is massless. And I proved it by using a spontaneous symmetry breaking and the Goldstone-Nambu theorem. And I quickly wrote this paper, sent it off, and then just as quickly discovered that it was totally wrong. The paper looked like it had a good proof in it. You went through the proof, and at every stage of the proof it seemed to be right, but in fact when you looked at it very carefully, you discovered there was no time-independent charge as was assumed, and therefore there could be no Nambu-Goldstone theorem, even though it looked like there was. And so I quickly realized that I'd sent off a wrong paper. The Nambu-Goldstone theorem, in fact, could be invalid in gauge theories, even though it looked like it was valid formally, but when you actually examined it carefully, the charge you thought was conserved didn't actually converge because integrals leaked out to infinity that you would normally throw away. And so at that stage, this was in April of 1964, at this stage, after I'd sent out a wrong paper to Physrev Letters, which I expected to get back so I could correct, but I never saw it again, I realized that you could easily write down theories that looked like they had a Goldstone theorem, but did not, as long as they were gauge theory. This was an important paper. Now it's mostly unnoticed, and it does have an error in it, but there's an irony to it. The error is very subtle, and about a month later, Physics Letters received a paper by Peter Higgs. Now, I had used my error very skillfully to prove that the photon had zero mass. Peter Higgs used the same error, coming to in a slightly different mode, to come to a more satisfactory conclusion that it was probably possible to produce mass in theories that had gauge particles in it. Nevertheless, his paper also was wrong. The basic premise of the analysis was incorrect. And again, that shows the power of subtly wrong proofs. You can probably, if you're clever enough and skillful enough, you can probably produce any answer that you want. The Higgs paper is quite famous. My paper is not. I'm not sure if I'm happy about that or not, but probably. So that's sort of the beginning. My paper was certainly the first paper that was published that led towards the final conclusions that were reached. And this had a process of evolution. Okay. Now, the understanding of this oversight, I was very embarrassed. I had not, they will fairly disavow all blame, but I quickly went to Hagen and Kibble and realized I really needed help. And we talked about all of this, and we put it all together, and we wrote what is now the GHK paper, the Guralnik, Hagen, Kibble paper, on symmetry breaking. Now, I've written down here, I don't want to take the time to talk about, how am I doing on time? Okay, so I've written down here the proof that I had in the wrong paper. And you see, I wrote down what looks like a very strange but conserved current. But that current is the one that fails. In any event, so those are the words that I said. But in any event, Hagen, Kibble, and I wrote down the paper. Wrote down a model, which was a variant of the Bowler-Gilbert model that I mentioned. It was simply scalar electrodynamics. But we looked for a symmetry breaking solution of that model in an approximation and found that solution. Now that solution had no zero mass photon in it. It also had no charged scalar boson, because, as you all understand now, what had been the charged scalar boson, one component of it combined with the 2 degrees of freedom of the vector meson to make a massive vector meson, and the one remaining component is what's now called the Higgs boson. Now, we examined this model in the radiation gauge, which is a gauge that cuts out all the extraneous degrees of freedom and doesn't look manifestly Lorentz invariant, but is Lorentz invariant, but looks terrible. And we examined it there and verified how the degrees of freedom behave. But then we also examined it in an arbitrary gauge, and there we discovered, not surprisingly, that there were massless particles, because the manifest covariance of an arbitrary gauge demands that the Goldstone theorem is obeyed. When you have manifest Lorentz invariance theory, the causality forces forces all the charges to actually be time independent. And what we discovered was that in the manifestly covariant arbitrary gauge theory, that you had Goldstone bosons, but those Goldstone bosons were all as pure gauge in nature, so they weren't anything that was physically measurable. And the physical stuff was very simply a massive vector particle and a free scalar particle. Well, we worked all this out, and essentially this was all done in April, but we were justifiably scared because I had shown twice you could have a totally convincing theory that was totally wrong. And so we held on to it for quite a long time, checking and rechecking, talking with a lot of people coming through Imperial College, all of whom told us it was wrong. And so we were very reluctant to publish it. But what we finally did, obviously. Now, I should say something about this paper. It had what's called the Higgs mechanism, namely the general proof that that the Goldstone theorem is not valid, independent of the model. Very generally, stated in the paper, much more generally stated a few months later in the talk that I gave, that there was a mechanism and then there was a specific model. And that paper and our follow-up statements are actually the only analysis that I know of that existed at the time, or even now, showing that as a general phenomena that there is what's called a Higgs mechanism, and then that the model itself that we produce, which is the same as the model produced by our surprise, we discovered as we were sending the paper out the door, by Higgs and Broad and Englert, the model is essentially the same, except our model is a little different than ours. Than theirs superficially, because the model, I wrote down the action there, if you look at it, that model doesn't have a quartic interaction in it. If you look, for example, at Higgs's paper, his paper puts in an explicit quartic interaction. Now, in fact, that makes no difference, but you have to iterate the model beyond the first leading approximation, which is what's in all the books and mostly is what people look at. And the reason it makes no difference, it has to do with what was the Harvard philosophy about how you write down a theory. And you never, ever, according to Schwinger's philosophy at the time, you never ever put in counter terms in the Lagrangian. There are counter terms, that's something that's just as naturally subsumed as you calculate higher and higher order versions of the theory. Now that's a very good philosophy when you're calculating out of perturbation theory, when you're doing a general calculation. And so we didn't put in, we could have still put in a quartic term, but we didn't. The quartic term is always induced. Now that produced something which we've been, I should say, we have been being beat up on lately by bloggers and colloquium, because they say, well, our model is not a real model of the Higgs boson because the boson in our model, our leading order solution, as you can see by, there's a light somewhere here. Well, you can see there, our leading order solution for what becomes a Higgs boson describes a particle which has zero mass. But there's nothing in the model that constrains the mass. Okay, the Goldstone theorem, if it were valid, would put a constraint on the mass. But in general, in a field theory, if you calculate a low order, then you calculate next orders, there are corrections to the mass. Masses are things that vary. It's only when there's a specific symmetry or some sort of constraint that masses don't vary. And in general, if you don't have such a constraint and you calculate in a field theory and you don't allow the mass to vary, the theory turns out, I can't prove a theorem, but in general you'll find that the theory actually turns out to be free. You can't constrain the mass. And as you calculate higher orders to this theory, the mass associated with what's called the Higgs boson does change. And in fact, again, and this is experimentalists understand well, as everyone understands well, this is no surprise. The model and our models do not, through the model itself, tell you what the mass of the Higgs boson is. That's in part why it's hard to look for. You have to try to constrain it by other physical observations. But the model itself does not tell you about the mass. That you have to put in by hand, and that in turn, evaluating other parameters, and that in turn sets the symmetry breaking parameter, or the couplings, and that in turn feeds through to the other masses to which have mass given to them associated with the Higgs boson. So, as I say, we've been being slammed on that. It's both irritating and amusing to find that 50-year-old work is still controversial. So I guess that I'm essentially out of time. I should just mention that I was going to make some comments about Higgs's paper. And as long as there's criticism going around, you should all look at Peter Higgs's paper. It's a very good paper, don't get me wrong. It's beautiful work. However, if you look to his solutions, to his equations, he doesn't work in any gauge. And and his model is classical. And he writes down a solution which has a massive boson in it. However, if you look at his equations, you'll discover he has not written down the full solutions to his equations. And not only does his model, which is an arbitrary gauge, have a massive boson in it, but it also has massless particles. And he should have addressed these. Because those massless particles, now that's not wrong. He didn't write it down, but he should have written them down. He would have been forced to if he had a quantum theory. He should have, even in a classical theory. They're part of the solutions to the differential equations. But those have to be there because of the Goldstone theorem, which is valid at any gauge, as long as it's not the radiation gauge. That is, it's valid at any what's called manifestly covariant gauge. And he doesn't write that down. If he'd written down the full solution, he would have had the obligation to explain that those massless particles are not something that you experimentalists should look for, but they're purely gauge in nature, so you can't evolve them. So this whole thing is actually, even now, very subtle. And one has to truly be very careful. And I know for sure of only one book that gets this right. So our students are being taught wrong. Now, you could argue it doesn't make any difference, but it does make a difference if you're really trying to understand a theory and you want to produce another theory and you really want to understand all this. You really need to be careful. And what held us up in all of this was it is really quite subtle. And even now, it is quite subtle and quite interesting. And I'll just end by just saying that there are, after the Englert, Braud, Higgs, Guralnik, Higg, and Kill paper, there are two more papers which are important. There is a paper by me that was my standard talk of the time, which was given at a conference for Heisenberg in Feldafing, a little village outside of Munich, and a paper where I was really beat up and told in private, so it wasn't publicly embarrassing, but I was told by Heisenberg, in this case he was not uncertain, he was told with certainty that I didn't understand physics, which was undoubtedly true. And he very much scared me, and I thought it was the end of me as a physicist. I did manage to survive. But anyway, that paper is published and has a much more explanation in it than our Guralnik, Higg, and Kibble paper. It was published in conference proceedings, which you can find in many libraries, but now is listed as a rare book. And I recently reprinted it. And following that, after that talk, it was a standard speech I gave all around, including at Edinburgh. And after that talk, Higgs wrote a famous paper in Physical Review. And the first part of that paper is very close to being identical to my talk. And in fairness to him, he does reference us and conversations with me. The second part of the paper has some tree model calculations, which is something that we didn't publish. So finally, this did pay off for us. This is at the APS meeting in 2010, where 6 of us got a Sakurai Prize. Peter couldn't make it. There's Tom Kibble on the left. I'm in the middle. There's Hagen on the right. You see I'm surrounded by giants. Englert and Braud, who sadly died last year, so we didn't get to hear these wonderful results. All right, I thank you.
The time is for questions, please. Jiří.
Did you know at that time the close similarity between the getting mass to a gauge particle and between what happens in superconductivity? I mean the Meissner effect. Because
the answer is no, we did not.
But there was a paper by Anderson.
We were told that there was an issue. Now, we did find out after we'd done this about Anderson's paper. Now Anderson's paper, I should point out to you, one does not have a Higgs boson, two does not have any of this mathematics, is not relativistic, and relies on the experimental observation and says the same thing must happen in high energy physics. So again, judge it for what it's worth. Anderson's a brilliant man, but we did not know about it at the time.
Further questions? If not, I have a question to comment. At the beginning of your talk, you talk about a number on an Arsenio paper. In their case, it was not a gauge symmetry, it was a chiral symmetry. It was spontaneously broken. And I think
there wasn't gauge symmetry.
And I think in their case, this goes to water actually quite useful because it's a pion. It's not exactly, approximately, but I think they acknowledge the fact that the idea is good to produce even a physical particle which is not exactly goes to water, pseudo goes to water, a very finite mass. So this, actually, these ghosts on water are not always useless. They are all sometimes useful.
Oh yeah, no, it's a very, very interesting paper because, again, it shows, I wouldn't quite say it's duality, but it shows there's many ways to approach the same theory. And it's a very, very valuable and very interesting paper.